Every time you point at a rainbow and share the view with a friend, you are technically lying to them, because no two people in the history of Earth have ever seen the exact same rainbow. What looks like a giant, colorful arch floating in the sky is actually a personalized optical illusion created specifically for your exact eyeballs, and you are missing half of the show every single time. Rainbows are not physical objects hanging in space. They are dynamic geometry games played between the sun, falling water drops, and your brain. If you move one step to the left, your rainbow moves one step to the left. If you chase the end of it to find a pot of gold, it retreats at the exact same speed. Because the end of a rainbow does not exist in a physical location. It only exists in the precise relationship between the light and you. In fact, the biggest myth about rainbows starts with their shape. We call them rainbows, arches, or semicircles. But in reality, every single rainbow is a complete 360-degree circle. The only reason you usually see an arch is because the ground gets in the way, like a giant party pooper. When you stand on the flat earth, the bottom half of the circle is blocked by the soil beneath your feet. But if you hop on an airplane or stand on the edge of a high cliff with mist below you, the horizon drops away, revealing the full, breathtaking circular ring floating in midair. So how does a sky full of chaotic, random falling water droplets manage to organize sunlight into a crisp, perfectly ordered ring of color? The secret starts inside a single drop of rain, where light undergoes a microscopic highway collision that slows down the universe. Light travels through empty space at roughly 186,000 miles per second. But the moment a ray of sunlight hits a round droplet of water hanging in the atmosphere, it hits a speed bump. Water is denser than air, so the light slows down instantly. This sudden deceleration forces the light to bend, a process scientists call refraction. Now, sunlight might look plain white to your eyes, but white light is actually a chaotic crowd of all the colors of the visible spectrum traveling together. Each color travels at a slightly different wavelength, which means each color slows down and bends by a slightly different amount when entering water. Violet light has shorter wavelengths and bends the hardest, while red light has longer wavelengths and bends the least. This splitting process is called dispersion. The single droplet acts like a tiny glass prism, forcing the uniform white beam to unpack its bags and display every individual color hidden inside. Once the light enters the water drop and splits, it travels through the liquid until it hits the back wall of the droplet. Here, instead of popping out the back, a huge chunk of the light bounces off the internal surface like a basketball hitting a backboard. This internal reflection bounces the light back toward the front of the droplet. As the light exits back out into the air, it speeds up again and bends one more time, sending a fan of brilliant separated colors racing out toward the world. Now, here is where the pure geometry gets fascinating. Millions of raindrops are falling at different speeds and different positions, bouncing light everywhere. So why do you see a smooth, focused ring instead of a blurry, messy cloud of colors? The answer comes down to one specific magic number: 42. When sunlight bounces inside a spherical raindrop and exits, the maximum concentration of light comes out at a very specific angle relative to the incoming sunlight. For red light, that exit angle is precisely 42 degrees. For violet light, it is 40 degrees. Every drop of water in the sky is blasting out tiny color rays in all directions, but you only see the bright colors from the drops that are sitting at the exact right angle relative to your eyes and the sun behind you. To picture this, imagine an invisible cone stretching out from your eyes into the sky. The center of this cone is an imaginary line running straight from the sun, through your head, and out into the darkness ahead of you. Any droplet that falls exactly on the outer edge of a 42-degree angle from that central line will direct red light straight into your pupils. Any droplet sitting at a 40-degree angle will shoot violet light straight into your pupils. Because 42 degrees is a fixed angle in 3D space around your line of sight, all the droplets that can send light to your eyes form a perfect circle in the sky. If you stand next to a friend, their eyes are located a few feet away from yours. That means their personal vision cone hits a completely different set of raindrops than your vision cone. You are viewing one set of water droplets bouncing light at 42 degrees, and your friend is viewing an entirely different set of droplets a few feet over. You are literally living in your own personal optical universe. Now, what happens when nature decides to flex and hit you with a double rainbow? Double rainbows are not just faint echoes or magical glitches in the simulation. They are created when sunlight bounces inside a raindrop not once, but 2 times. Light enters the droplet, bends, bounces off the back wall, travels across the drop, bounces off the inside wall a second time, and then exits back into the air. Because of that extra internal bounce, 2 incredible things happen. First, the double bounce flips the order of the colors upside down. In a primary rainbow, red is on the outside at 42 degrees and violet is on the inside at 40 degrees. But in the secondary rainbow, which forms at a wider angle around 51 degrees, the color order is inverted. Red is on the inside and violet is on the outside, creating a mirrored color arrangement in the sky. Second, that second bounce drains energy from the light, making the secondary rainbow look about 10 to 20% fainter than the primary one. But if you look closely between the primary rainbow at 42 degrees and the secondary rainbow at 51 degrees, you will spot something even weirder. The strip of sky sitting between the 2 bows is noticeably darker than the rest of the sky. It looks almost like a dark shadow band stretched across the clouds. This eerie gap is known as Alexander's dark band, named after the ancient Greek philosopher Alexander of Aphrodisias, who first described it in the year 200. The dark band exists because of raw angle math. Raindrops in the 42-degree region bend light toward your eyes to form the first rainbow. Raindrops in the 51-degree region bend light toward your eyes to form the second rainbow. But the drops hanging in the dead zone between 42 and 51 degrees cannot reflect light into your eyes at all. They bounce sunlight away into other directions, leaving that specific strip of sky completely stripped of redirected light. You are literally looking at a region of the sky where light has been diverted away from you. If you think that is cool, look even closer at the very inner edge of a vibrant rainbow next time you see a bright bow. Sometimes you will notice faint, delicate, pink and green bands repeating just underneath the main violet ring. These supernumerary bows were a massive headache for classical physicists for centuries because standard ray optics, treating light like simple straight laser beams, could not explain why they existed. The secret behind these extra bands revealed something fundamental about reality. Light is not just particles traveling in straight rays. Light behaves as a wave. When sunlight bounces inside microscopic raindrops that are extremely small and uniform in size, the light waves exiting the drop overlap with each other. If the crest of one light wave aligns with the crest of another, they amplify each other, creating a bright band of color. But if the crest of one wave aligns with the trough of another, they cancel each other out, leaving a dark gap. This phenomenon, known as wave interference, creates tiny alternating stripes of light and dark bands inside the main rainbow ring. You are effectively watching quantum wave mechanics play out on a canvas thousands of feet wide in the sky. What determines how sharp and vivid a rainbow looks? It all comes down to the physical size of the water droplets. Large rain droplets, around 1 to 2 millimeters wide, act like high-quality optical lenses, creating razor-sharp separations between colors and generating bright, intensely saturated rainbows. But if the water drops get smaller and smaller, like in a fine mist or heavy fog, where droplets are less than 0.05 millimeters wide, diffraction takes over. The light waves smear out and overlap so much that the distinct color bands blur together into a spooky, ghostly white halo called a fogbow. There is another strange phenomenon that happens under rare weather conditions: moonbows. Yes, night rainbows actually exist. When the full moon shines bright on a humid night or near a roaring waterfall, lunar light can hit raindrops and produce a lunar rainbow. But because human eyes use specialized cone cells for color detection that require bright light, night rainbows usually look like eerie, ghostly white rings to the human eye. Your camera, however, using a long exposure, can capture the full, vibrant red, yellow, and blue hues hidden in the moonlight. So the next time you see a rainbow painting the sky after a summer storm, take a second to appreciate what is actually happening. You are not looking at a static object painted on the clouds. You are standing at the apex of a massive geometric cone, surrounded by billions of microscopic water drops, each acting as a precision optical instrument, slowing down, splitting, and redirecting light rays at exact 42-degree angles straight into your retina. Nature is serving up a custom one-of-one light performance, tailored exclusively to your precise position on planet Earth. Nobody else can see what you are seeing, and the moment you take a single step, the entire show rebuilds itself around you. Have you ever been lucky enough to spot a full, circular rainbow from an airplane or a high mountain peak? Or have you seen a double rainbow with Alexander's dark band in person? Let me know in the comments below. I would love to hear your story. If you found this trip through the hidden physics of light fascinating, hit that like button, share this video with a friend, and subscribe to the channel for more deep dives into the hidden mechanics of our universe. Thanks for watching, and keep looking up.